Somewhere above your head right now, a photon just left a star. It crossed the entire visible universe to reach the back of your eye. And according to the laws of physics, as strange as this sounds, that photon experienced none of the journey. Not a fraction of a second. Not a single moment. As far as light itself is concerned, it did not travel at all. It left and arrived in the same instant, from its own point of view, even though for you, standing here on Earth, that journey may have taken millions of years. This isn't a metaphor. It isn't poetic language dressed up for a documentary. It is one of the most rigorously tested, mathematically unavoidable conclusions in modern physics. And it comes from a theory so well confirmed that it underlies the GPS satellite in your pocket, the particle accelerators buried under Geneva, and the very structure of cause and effect in this universe. Today we're going to prove step by step, using nothing but established peer-reviewed physics, why light does not move through space the way you have been taught to imagine it. And by the end, you will understand something that even most science documentaries get quietly wrong. Let's start with the assumption almost everyone carries without ever questioning it. We picture light like a tiny bullet. It leaves a source, it flies through the vacuum of space, it covers distance, and after some measurable amount of time, it hits a target. This is how light behaves in almost every classroom diagram, every animation, every popular explainer. A photon leaves the sun. 8 minutes and 20 seconds later, by the clock on your wall, it lands on your skin as warmth. That part is true. From our frame of reference, sitting on Earth, that photon absolutely takes 8 minutes and 20 seconds to arrive. Nobody is disputing the measured travel time as we experience it. What's being challenged is the assumption that time and distance mean the same thing to light as they mean to us. And that assumption falls apart the moment you take Einstein's theory of special relativity seriously and actually run the mathematics for an object moving at the speed of light, rather than just near it. In 1905, Albert Einstein published a paper that would eventually dismantle the idea of absolute time and absolute space, replacing it with something far stranger and far more elegant. The core insight was this: time is not the same for every observer. It depends on how fast you're moving relative to someone else. This isn't philosophy, it's measurable. Muons, unstable subatomic particles created when cosmic rays slam into our atmosphere, should decay long before they ever reach the ground, based on their incredibly short half-life. And yet, detectors on Earth's surface pick them up constantly. Why? Because they are moving close to the speed of light, and from our frame, their internal clocks are running slower. Time dilation isn't a thought experiment anymore. It has been measured directly, repeatedly, in particle accelerators and in atomic clocks flown on airplanes, matching Einstein's predictions to extraordinary precision. Here's where it gets interesting for light specifically. Einstein's equations include something called the Lorentz factor, a mathematical term that describes exactly how much time slows down and how much length contracts for an object as its speed increases relative to an observer. At low speeds, this factor is negligible. Your car, your plane, even a rocket leaving Earth, the effect is real but tiny. But as an object's speed approaches the speed of light, the Lorentz factor grows toward infinity. Time dilation becomes extreme. Length contraction becomes extreme. And when you plug in the actual speed of light itself into this equation, something remarkable happens mathematically. The factor doesn't just get large. It becomes undefined in the ordinary sense, because you're dividing by zero. Physicists interpret this specific result as meaning that for a hypothetical observer moving at exactly the speed of light, the passage of time and the extent of space both collapse to zero. Now, an important clarification, one that most physicists insist on, and one that separates rigorous science from oversimplified sensationalism. Light does not have a valid reference frame in the way you or I do. You cannot literally sit on a photon and watch a stopwatch, because the entire framework of relativity breaks down at that exact limit. This is why serious physicists describe the zero proper time result as a limiting case rather than a literal experience light has. But the mathematics leading up to that limit is completely solid, and it tells us something undeniable about the nature of light's relationship to space and time. As you take any massive object and accelerate it closer and closer to light speed, its experience time drops towards zero, and the distance it perceives itself traveling shrinks towards zero. Light, moving through the vacuum at that ultimate speed limit, sits exactly at that boundary. From any perspective that could meaningfully be called light's own, the journey is not merely fast. It is not extended in time or space at all. This concept has a name in physics: proper time, sometimes written as tau. Proper time is the time experienced by an object along its own path through spacetime, as opposed to coordinate time, which is what an outside observer measures. For you and me, walking around on Earth, our proper time and the time on wall clocks around us line up closely enough that we never notice a difference. But proper time is calculated using what's called a spacetime interval, a quantity that combines space and time into a single measurement, first formalized by the mathematician Hermann Minkowski, who had been Einstein's teacher and who, in a now famous 1908 lecture, declared that space and time by themselves were doomed to fade into mere shadows, and only a union of the two would preserve an independent reality. Minkowski wasn't being poetic. He had discovered that Einstein's relativity could be expressed geometrically as a four-dimensional structure called spacetime. And within that structure, the paths that light takes have a very specific, very strange property. They are called null geodesics, and along a null geodesic, the spacetime interval is exactly zero. Let that sit for a moment, because this is the actual proof, the mathematical backbone behind the claim in our title. In ordinary geometry, if you walk from point A to point B, the distance between those points is positive, and it doesn't matter who's measuring it. In the four-dimensional geometry of spacetime, the equivalent quantity, the interval, isn't just about spatial distance. It also involves the passage of time, combined through the mathematics of relativity. For anything moving slower than light, this interval works out to be what physicists call time-like. For anything faster, hypothetically, it would be space-like. But for light itself, moving at exactly c, the interval is null, zero. Not small, not negligible, zero. And because proper time is derived directly from this interval, the proper time elapsed for a photon traveling any distance, whether it's a few meters across a room or 14 billion light-years across the observable universe, is exactly the same. Zero. This is not a fringe interpretation. It's found in standard relativity textbooks used at MIT, Caltech, and Stanford. Edwin Taylor and John Archibald Wheeler, in their classic textbook Spacetime Physics, walk students through exactly this calculation, showing that light's world line has zero proper length. Wheeler, incidentally, is the same physicist who coined the term black hole, and who spent decades exploring the deep geometric consequences of Einstein's work. This isn't a case of one scientist making a bold claim that others dispute. It's baked into the very mathematics that predicts the GPS corrections your phone relies on every single day. The mathematics that has been checked against particle physics experiments at CERN for over half a century. The mathematics that correctly predicted the bending of starlight around the Sun during the 1919 eclipse expedition led by Arthur Eddington, an observation that turned Einstein into a household name almost overnight. So here is the reversal at the heart of this investigation. We've been taught to think of light as the fastest possible traveler, crossing the universe on an epic journey lasting millions or billions of years. And in our frame, that description is completely accurate. We measure that time. We build telescopes based on it. When astronomers look at a galaxy 14 billion light-years away, they are correctly describing that light as ancient, as having crossed an almost incomprehensible gulf of space and time to reach us. But from the only perspective that could ever be attributed to the light itself, no time passes and no distance is crossed, because the entire concept of separation between departure and arrival collapses at the speed of light. Light isn't a marathon runner logging billions of years of travel. In its own geometric relationship to spacetime, departure and arrival are the same event, connected by an interval of exactly zero. Now, if this were the entire story, it would already be a fascinating case file to close. But there's a second angle of proof, distinct from the proper time argument, that reinforces the same conclusion from a completely different direction: length contraction. Special relativity tells us that an object moving relative to an observer appears contracted along its direction of motion, according to that same Lorentz factor we discussed earlier. This has been measured in practice using fast-moving particles at accelerator facilities, where their fields appear flattened into pancake-like shapes, exactly as predicted. As velocity increases toward the speed of light, contraction increases too, and in the theoretical limit at c, the length of the path being traveled, as measured from what would be light's own frame, shrinks to zero. If proper time gives us zero elapsed time for light, length contraction gives us zero elapsed distance. Two completely independent lines of mathematical reasoning, one built from the geometry of time, the other from the geometry of space, arrive at the identical conclusion. From any frame that could be attributed to light, the journey has no duration and no length. At this point you might reasonably ask, If this is true, how does light manage to carry information at all? How does the sun's light warm your face, or a distant supernova's light get captured by the Hubble Space Telescope, if there's no meaningful sense in which light travels the way we picture it? This is where our investigation needs to make a careful distinction, because this is exactly the point where popular science content tends to oversimplify and mislead. From our frame, the observer's frame, light absolutely does propagate through space in a way that's fully consistent with cause and effect. The photon from the sun genuinely interacts with your skin approximately 8 minutes and 20 seconds after it left the solar surface. And that time delay is not an illusion. It has real physical consequences. If the sun vanished right now, you would still see it in the sky and feel its heat for over 8 minutes, because the information hasn't reached you yet. This delay is why astronomers describe deep space observations as looking back in time. When the James Webb Space Telescope captures light from galaxies formed shortly after the Big Bang, it is genuinely receiving photons that departed those galaxies over 13 billion years ago. And that measured coordinate time journey is completely real and foundational to how we understand cosmic history. So what reconciles these two seemingly contradictory truths? The answer lies in something relativity insists on again and again. Physical reality isn't a single universal narrative. It's frame-dependent, and different valid descriptions can both be true without contradicting each other, as long as you're careful about whose frame you're describing. From our frame, light takes measurable, meaningful time to cross measurable, meaningful distance. And this description is not wrong. It's how the universe presents itself to observers moving slower than light, which includes every human being, every telescope, and every measuring device ever built. But if you try to extend that description into a frame attributed to the light itself, the mathematics doesn't just get complicated, it becomes physically meaningless in the conventional sense, because no valid rest frame exists for something moving at exactly the speed of light. Physicists like Sean Carroll, a theoretical physicist at Caltech, known for his public explanations of relativity, has pointed out in lectures and writing that the light has no time description, while mathematically well motivated, has to be handled carefully, since strictly speaking you cannot construct a reference frame that travels alongside a photon using the standard Lorentz transformations, precisely because those transformations become singular at v equals c. This is the honest, rigorous version of the claim, not the version that pretends light experiences a subjective journey, but the version that recognizes the null interval as a real geometric fact about light's path through spacetime, one that simply cannot be translated into an experience the way we experience time. This brings us to the reality check at the center of this entire case file. Light does not move through space in the way a bullet, a car, or even a spacecraft move through space, covering ground while a clock ticks forward for it in any meaningful physical sense. Light's relationship to spacetime is fundamentally different from every massive object we've ever measured. Its path is what's called a null geodesic, an interval of exactly zero connecting every point along its journey, meaning that in the deepest geometric sense, travel as we understand the word, motion through an extended duration across an extended distance, simply does not apply to light the way it applies to us. And yet, simultaneously, from the frame that you and I actually occupy, light unmistakably propagates, unmistakably takes time, and unmistakably crosses real distances that we can measure with extraordinary precision, using tools like laser ranging experiments bounced off retroreflectors left on the moon by the Apollo missions. Experiments that have measured the Earth-Moon distance to within centimeters by timing the round trip of laser pulses. Both descriptions are correct, neither cancels the other out. This is not a contradiction in physics, it's a demonstration of exactly why Einstein's relativity was so revolutionary, because it revealed that questions like how long did this take and how far did this travel don't have single universal answers independent of who's asking. There's a related piece of this puzzle worth addressing directly, because skeptical viewers, and we know many of you are exactly that kind of skeptical, critical thinker, will rightly wonder about it. The difference between phase velocity and group velocity, and how that connects to previous investigations on this channel into experiments where light has been dramatically slowed down. In 1999, physicist Lene Hau and her team at Harvard University succeeded in slowing light to a speed of just 17 meters per second by passing it through an ultra-cold cloud of sodium atoms called a Bose-Einstein condensate. And in later experiments, her team managed to bring light to a complete, if temporary, stop, storing its information in the quantum states of the atoms themselves before releasing it again. This might seem to contradict everything we've just established about light's invariant speed, but it doesn't, and understanding why actually deepens the proof we're building here, rather than undermining it. What Howe's experiments slowed down was the group velocity of light, the speed at which the overall envelope and information content of a light pulse moves through a medium, which absolutely can be altered by the interaction between light and matter. The speed of light in a vacuum, the fundamental constant c that appears throughout Einstein's equations, remains untouched and unchanged in Howe's experiments. Individual photons interacting with atoms in the condensate are still fundamentally governed by the same relativistic rules. What changes is a collective, emergent behavior of light interacting with dense matter, not the underlying null geodesic nature of light's path through spacetime in vacuum. This distinction between light's behavior in a vacuum, where relativity's strict rules apply in their purest form, and light's behavior when interacting with matter, where its effective speed can be manipulated dramatically, is essential to understanding why both sets of experiments can be true at once. Let's also address the objection a sharp viewer might raise. Doesn't quantum mechanics complicate this picture even further? The honest answer is yes. And it's worth being transparent about where the edges of current understanding actually sit, rather than pretending physics has this all wrapped up with no open questions. In quantum electrodynamics, the theory developed largely by Richard Feynman, Julian Schwinger, and Shinichiro Tomonaga, work that earned them the Nobel Prize in Physics in 1965, light is described not just as a wave following a single path through spacetime, but as a particle, a photon, whose behavior must be calculated by summing over every conceivable path it could take between 2 points, weighted by probability. Feynman's own popular explanation of this in his book QED, The Strange Theory of Light and Matter, makes clear that photons do not travel in the simple straight-line, single-path way our everyday intuition suggests, even before we bring relativity into the picture. Feynman describes the reflection of light off a mirror, showing that light doesn't just take the single path predicted by classical optics, the path where the angle of incidence equals the angle of reflection, but that in principle its probability amplitude includes contributions from every possible path, most of which cancel out through interference, leaving only the paths near the classical one to constructively reinforce. This deep quantum weirdness exists layered on top of the relativistic weirdness we've been discussing. And reconciling quantum mechanics with general relativity fully into a single working theory of quantum gravity remains one of the biggest unsolved problems in theoretical physics today, an active area of research involving approaches like string theory and loop quantum gravity, neither of which has yet been experimentally confirmed. We mention this not to undercut the case we've built, which rests on extremely well-established special relativity, but to be honest about where solid, tested science ends and open frontier research begins. Because credibility on this channel always means drawing that line clearly. Coming back to firmer ground, there's one more critical piece of evidence worth walking through, because it shows just how seriously the physics community takes the zero proper time result. Not as an interesting curiosity, but as a load-bearing pillar of modern technology. The global positioning system, the network of satellites that lets your phone tell you exactly where you are on Earth, depends on atomic clocks in orbit that must be corrected for relativistic effects, both the time dilation from their orbital velocity and the time dilation from being farther from Earth's gravitational well, an effect described by general relativity rather than special relativity. If engineers had ignored Einstein's equations, GPS positioning would drift by several kilometers within a single day, according to calculations confirmed repeatedly by the US Air Force and civilian agencies operating these satellite systems. This isn't a photon moving at the speed of light we are correcting for here, granted. It's clocks moving at orbital velocities far below light speed. But it's the same underlying mathematical framework, the same Lorentz factor, the same space-time geometry that, when you push the equations all the way to their limit at v equals c, produces the zero proper time, zero length contraction result for light that we've spent this investigation proving. In other words, the very same equations that keep your phone's map accurate to within a few meters are the equations that tell us light does not experience travel through space the way massive objects do. This is not speculative physics dressed up for a documentary. It's the same trusted mathematics underpinning navigation systems used by militaries, airlines, and everyday commuters across the entire planet. So what does all of this actually mean for how we should think about the universe and about our place within it, staring up at a night sky full of ancient light? It means that when you look at a star, you are witnessing two simultaneous, equally valid truths. In your frame, that light has been traveling, in the fullest sense of the word, for years, centuries, or millennia, crossing an almost unimaginable gulf of space, aging as it goes in every way we can measure with clocks and rulers built from atoms just like the ones in your own body. And in the only frame that could ever be attributed to that light itself, a frame that formally doesn't exist in the way our frames do, but whose limiting mathematics is undeniable, no time passed at all, and no distance was crossed at all. Departure and arrival, for light, are not separated events. They are, in the deepest geometric sense special relativity can describe, the same event. This is why serious physicists, when pressed carefully, will describe light's journey using phrases like "the entire universe from edge to edge is a single point for a photon." A description that sounds almost mystical, but that emerges directly and rigorously from equations tested in laboratories, satellites, and particle accelerators around the world for over a century. This idea reshapes something deeper than just how we think about photons. It reshapes how we think about causality itself, the very structure of cause and effect that holds the universe together in a coherent, sequential order. Because light moves along these null geodesics, along paths of exactly zero interval, it defines the absolute boundary of what can possibly influence what, in Minkowski's geometric language, the edge of every event's light cone. Nothing with mass can reach or exceed this boundary, according to everything we verified experimentally, which is precisely why the speed of light functions not just as a property of light itself, but as the universe's fundamental speed limit for the transmission of information and influence. Every law of physics that respects causality, from electromagnetism to the strong and weak nuclear forces, to gravity itself, as confirmed by the 2015 detection of gravitational waves by the LIGO observatories arriving at Earth at exactly light speed, respects this same boundary. Light isn't simply fast. Light is the geometric marker of the edge of possibility itself, at every single point in the universe, at every single moment. Before we close this file, it's worth being clear about what we are not claiming, because credibility on this channel means drawing hard lines around speculation. We are not claiming that photons possess consciousness or subjective experience of any kind, a claim that occasionally circulates in pseudoscientific corners of the internet and that has no basis in physics whatsoever. We are not claiming that the standard, measured travel time of light across the universe, the very foundation of modern astronomy and cosmology, is somehow false or illusory. It remains completely real and essential to how telescopes function and how we reconstruct cosmic history. What we are claiming, and what the mathematics of special relativity unambiguously supports, is that the geometric relationship between light and spacetime is categorically different from the relationship any massive object has with spacetime. And that difference is captured precisely by the null interval along light's path, by the zero proper time result derived from Einstein's own field-tested equations, and by the length contraction that reaches its own zero in that same theoretical limit. This is rigorous, mainstream textbook physics, not fringe speculation, even though it produces a conclusion strange enough to sound like something out of science fiction. There's one final layer to this case file worth examining closely, because it connects everything we've established to the oldest light humanity has ever detected. The cosmic microwave background, the faint afterglow of radiation left over from roughly 380,000 years after the Big Bang, was first identified by radio astronomers Arno Penzias and Robert Wilson in 1965. An accidental discovery that earned them the Nobel Prize in Physics and that remains one of the strongest pieces of evidence supporting the Big Bang model itself. That radiation has been traveling, in our frame, for approximately 13.8 billion years, stretched and cooled by the expansion of space itself, until it now appears not as visible light but as microwaves, detectable by satellites like the Cosmic Background Explorer and later the Planck spacecraft. Every single photon making up that ancient signal obeys the exact same null geodesic geometry we've walked through in this investigation. In our measured coordinate time frame, that radiation has crossed almost the entire observable universe and aged alongside it for nearly 14 billion years. And yet, in the same limiting geometric sense that applies to every photon everywhere, its own relationship to that journey collapses to zero, exactly as the mathematics demands. This is perhaps the most extreme example available to us of the exact paradox at the center of tonight's investigation, ancient light, older than every star in the sky, that in its own null interval never left its point of origin at all. It's a reminder that the strangeness we've uncovered here isn't a rare edge case confined to a hypothetical, isolated photon. It's a universal property of light itself, present in every ray of sunshine warming your skin, and in the oldest radiation the universe has ever produced. It also reframes something worth sitting with for a moment before we close this file. The question of whether light waits anywhere, whether there's some sense in which it experiences a cue, a delay, a passage through the intervening dark. The mathematics says no, categorically. There is no waiting room for light between departure and arrival, no interior experience of transit, because the very structure that would allow for such an experience, an extended proper time, a non-zero interval, simply is not present along a null geodesic. This is different from saying light is instantaneous in some mystical sense that violates causality. It emphatically does not, and nothing in this investigation should be read as suggesting information can outrun the speed limit that light itself defines. It simply means that the concept of duration, of an interior meanwhile, does not apply to light's own relationship with its path, even while that same path, measured from outside, from our frame, unfolds across measurable years, centuries, and eons that are every bit as real as the light streaming through your window right now. And that's really the heart of why this channel exists. Reality, when you actually dig into the evidence rather than settling for the comfortable, simplified version, is consistently stranger and more remarkable than any myth or misconception could ever be. Light crossing the universe while somehow experiencing zero time and zero distance isn't a trick of language or an internet oversimplification. It's a direct, provable consequence of the same theory that keeps your GPS accurate, that predicted the bending of starlight during a total solar eclipse, that correctly forecasts the decay rates of unstable particles screaming through our atmosphere at nearly the speed of light every single day. The next time you look up and see a star, remember that you're looking at something that, from its own impossible, mathematically limiting perspective, never actually left home at all. If this kind of evidence-based investigation into the hidden mechanics of our universe fascinates you as much as it fascinates us, make sure you're subscribed, because every case file we open on this channel follows the same rule. No myth stands unless the evidence backs it up, and no mystery gets left unresolved. We'll see you in the next investigation.